Today, I'm going to explain about the normal approximation to the binomial distribution. If x is a binomial random variable with parameter n and p, the standard normal random variable can be calculated by this equation. Why? Because np is the mu, right? The mean. And np by 1 minus p is the variance, sigma square. So, in the previous slide, the standardizing is x minus mu over sigma, right? So, this is the mu, and this is the sigma in the case of the binomial distribution. So, by using this equation, we can simply calculate the answer based on the normal approximation. And as I mentioned here, mu is np, and sigma square is np by 1 minus p. And the standardizing of the binomial random variable x can be calculated by this equation. To approximate a binomial probability with a normal distribution, a continuity correction should be applied as follows. The probability of x, when x is smaller than or equal to small x, should be equal to the probability of x when x is smaller than or equal to x plus 0.5. So in this case, 0.5 is the correction factor, okay? And I'm going to explain why we have to provide the correction factor in the next slide. So, this probability can be transferred to this equation, that is the probability of z. Z is the standard normal random variable, right? That is x plus 0.5 minus np over np 1 minus p. And the probability of x, when x is larger than small x here, this should be changed to this equation. The probability of x when x is larger than or equal to small x minus 0.5. In this case, minus 0.5 is also the correction factor. And this can be transformed to this equation. The probability of z when z is larger than or equal to x minus 0.5 minus np over root np by 1 minus p. This approximation exhibits a good result when the np is larger than 5 and n by 1 minus p is larger than 5. And I'm going to explain why we have to provide the correction factor in this slide. If a binomial distribution with n is equal to 10 and p is equal to 0.5, its mu and sigma are 5.0 and 1.58 respectively. And we can draw this figure based on this assumption. And y-axis indicates the probability mass function or the probability density function. And x-axis indicates the random variable. Okay? And in the case of the historical diagram, that expresses the binomial distribution. Okay? And the curve indicates the normal distribution. So in this case, mu is np, that is equal to 50 multiplied by 0.1, and 10 multiplied by 0.5, that equals to 5, right? And sigma square is np 1 minus p, right? Based on the previous binomial distribution, that is equal to 10 by 0.5 by 0.5, that equals to 2.5. Okay? So, the variance is equal to root 2.5, that equals to 1.58. And in this case, what is the probability density function of the normal distribution? That is, fx is equal to 1 over root 2 pi sigma exponential minus x minus mu square over 2 sigma square, right? That is the equation for the normal distribution when x is from minus infinite to infinite. So in this case, we know about the mu, and we know about the sigma square and the sigma, right? So we can calculate the probability density function according to x, right? So based on this equation, we can draw this normal distribution. And as you can see here, the normal distribution exhibits very similar behavior with the binomial distribution, right? Okay? So in this case, for example, we want to obtain the value, the probability of x when x is between 6 to 9. Okay? We are going to calculate this probability. And this is the random variable. And this is the probability mass function for the binomial distribution, and also the probability density function for the normal distribution, right? And we can draw this normal distribution first. This is mu is equal to 5, right? This is the normal distribution. And we have 6, 7, 8, 9 here. And we can draw the histodiagram here. This is the histodiagram. And if we calculate this probability based on the binomial distribution, that will be the probability of x when x is equal to 6, right? Plus the probability of x when x is equal to 7, and the probability of x when x is equal to 8, and the probability of x when x is equal to 9, right? Based on the binomial distribution. And this can be rewritten as the probability mass function of 6 and the probability mass function of 7 and F8 and F9, right? Right? Based on the binomial distribution. And what about this shaded area? Here is the F6, right? Right? So this shaded area will be F6 multiplied by, what is the width here? That is 1. So that is equal to F6, right? And based on this concept, we all calculated this shaded area, right? This will be F7 multiplied by 1, that is equal to F7. And this is also F8 multiplied by 1, that is equal to F8. That is also F9 multiplied by 1 equal to F9. So, based on this diagram, what is this? The probability of x is between 6 to 9, there will be this shaded area, right? Okay? And in this case, this shaded area is equal to this area, right? 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 because this part can fill this part, and this part can fill this part, and this part can fill this part, and this part can fill this part, right? So this shaded area is very close to the area under the normal distribution from, what is this? Here is 5.5, here is 9.5, right? So this is very close to the probability of x when x is between 5.5 to 9.5 when we use the normal distribution, okay? So in this case, we are going to use the appendix table based on the standardizing, right? But at the first time, we have to change the binomial distribution to the normal distribution, right? Right? And to improve the accuracy of this normal approximation, we have to provide minus 0.5 here, 5 here, and plus 0.5 here to improve the accuracy of the normal approximation. So this is called the correction factor, okay? Okay? So if we want to calculate the problem regarding the binomial distribution based on this normal approximation, we have to first provide the correction factor, okay, to both sides, and then we can use the standardizing method. So the areas of the normal distribution approximate the areas of the binomial with correction factor plus minus 0.5. And this is the example. Example 4-18. In a digital communication channel, assume that the number of bits received in error can be modeled by a binomial random variable. And assume that the probability that a bit is received in error is 0.00001 and n is equal to 16 by 10 to 6th power, okay? This is wrong. This is 10 to 6th power. So in this case, p is equal to 0.00001 and n is 16 by 10 to 6th power, okay? In the case, what is the probability that 150 or fewer errors occur based on the normal approximation? That is the question. So we have to calculate the probability of x when x is equal to or smaller than 150, right? Right? And in this case, we are going to use the normal approximation. So there will be changed to the probability of x when x is smaller than or equal to 150 plus 0.5, right? This is the correction factor, okay? And so this can be written as the probability of x when x is smaller than or equal to 150.5, okay? And in this case, we can change this to the probability of z is smaller than or equal to 150.5 minus, what is the mu here? Mu is 160, right? Because this is m by p, right? And the sigma will be, sigma square will be 160 as well, okay? This is np 1 minus p. If you calculate this equation, you can obtain 160. So this can be 150.5 minus 160 over root 160. Okay? So this is probability of z when z is smaller than or equal to minus 9.5 over 12.65, and this is equal to minus 0.75. Okay? So, based on this appendix table, okay, and we can simply calculate this value, right? That is equal to 0.227. Okay? So, based on the normal approximation and the appendix table, we can simply calculate the answer, okay, of this example. And this is another example. Consider the transmission of bits in the previous example 4-18. And to judge how well the normal approximation works, it is assumed that the n is equal to 50 bits are transmitted, and the probability of an error is p is equal to 0.1. And in this case, what is the probability that 2 or less errors occur? So we can calculate the exact value based on the binomial distribution, right? And also we can obtain the normal approximation value. And I'm going to compare these two values. Firstly, we have to calculate the probability of x when x is smaller than or equal to 2, right? Right? So, the probability of x when x is equal to 0 plus the probability of x when x is equal to 1 plus the probability of x when x is equal to 2. Okay? And in here, the n is 50 and p is equal to 0.1. And based on the equation of the binomial distribution, this can be rewritten as 50 by 0, right? Multiplied by 0.1 to 0th power by 0.9 to 50th power, right? This is the binomial distribution equation, right? And plus 50 by 1 multiplied by 0.1 by 0.9 to 49th power plus 50 by 2 by 0.1 square, 0.9 to 48th power. And we are going to calculate these three equations. This is A, this is B, and this is C. A will be 50 factorial over 0 factorial by 50 factorials, right? By 0.1 to 0th power by 0.9 to 50th power. This can be eliminated, right? And what is this? This is equal to 1. And this is also equal to 1, right? So this is just 0.9 to 50th power. So there will be 0.00515. Okay? And what about the B? 50 by 49 factorial over 1 factorial by 49 factorial by 0.1 by 0.9 to 49th power. Okay? This can be eliminated, so this will be 50 by 0.1 by 0.9 to 49th power. Okay? That is equal to 0.02863. Okay? And the C will be 50 by 49 by 48 factorial over 2 factorial by 48 factorials by 0.1 square by 0.9 to 48th power. So this can be eliminated, and this can be eliminated by dividing 50, and 25 will be left, right? So 25 by 49 by 0.1 square by 0.9 to 48th power, that is equal to 0.077943. So if you add all these three answers here, the final answer will be 0.112. Okay, approximately. So this is the exact value for this problem, okay, based on the binomial distribution. And also, I'm going to solve this problem based on the normal approximation. The probability of x when x is smaller than 2, that is equal to the probability of x when x is smaller than or equal to 2.5, right? Based on the correction factor, right? And this can be rewritten as the probability of z when z is smaller than or equal to 2.5 minus 5, right? Mu is equal to 50 by 0.1, that is 5, right? Right? So sigma square was 4.5, okay? This is MP by 1 minus P, okay? You can simply calculate. So this will be 2.5 minus 5 over root 4.5, okay? So that is equal to the probability of z when z is smaller than or equal to minus 1.18, okay? Okay? So by using the appendix table, this will be 0.119. Okay? Yet, actually there is a small difference between these two values, but we can simply use the normal approximation for simplicity. Okay? 그러니까 약간의 차이는 있지만 뒤에 보면은 이제 바이노미얼 디스트리뷰션으로 풀 수 없을 만한 굉장히 복잡한 것들이 나와요. 그거는 약간의 값의 차이는 있어도 노멀 어프록시메이션을 쓰면 굉장히 간단하게 계산이 되니까 이거를 그러니까 말 그대로 어프록시메이션이에요. 맞죠? 그래서 이걸 쓰면 됩니다. And I'm going to explain about the normal approximation to the Poisson distribution. And what is the Poisson distribution? When the number of trials increases infinitely, we can change the binomial distribution to the Poisson distribution, right? Do you remember that? So I'm going to explain about the normal approximation to the Poisson distribution in here. If x is a Poisson random variable with mean is equal to lambda, and also the variance is equal to lambda, right? That is the definition of the Poisson distribution, right? So in that case, the standard normal random variable z is equal to x minus mu, right? Over root sigma square, that is lambda, right? Because mu and mu and sigma square have the identical value of lambda here. So we can simply calculate the z based on this equation, okay? And this approximation also gives a good result when the lambda is larger than 5, normally. And this is the example, normal approximation to the Poisson distribution. And assume that the number of fine particles per meter of dust follows a Poisson distribution with a mean of 1,000. If a square meter of dust is analyzed, what is the probability that 950 or fewer fine particles are found? And also we can calculate this based on the Poisson distribution, and also we can use the normal approximation, right? We have two options here. And firstly, I'm going to calculate this example based on the Poisson distribution. In that case, the mean is 1,000, right? So the lambda is equal to 1,000, okay? So in this case, the number of fine particles are quite large, right? Because the mean value is 1,000. So we can use the Poisson distribution instead of the binomial distribution, right? So in the case, lambda is 1,000. And what is the probability mass function of the Poisson distribution? That is E minus lambda by lambda to x's power over x factorial, right? That is the equation for the Poisson distribution. And the question was, what is the probability that 950 or fewer fine particles are found? That is the probability of x, when x is smaller than or equal to 950, right? Right? So if we calculate this equation based on the Poisson distribution, there will be the summation of k is from 0 to 950 e minus 1,000 by 1,000 to k's power over k factorial, right? Right? So in that case, it is almost impossible to calculate this based on the scientific calculator by hand, right? 이거 손으로 계산할 수 있어요? 0부터 950번 다 더하는 거? 못하죠? 그죠? So in this case, we have to use the normal approximation, okay? It is too complicated. So we are going to use the normal approximation here. That is the probability of x when x is smaller than or equal to 950. But in this case, we don't have to use the correction factor, right? Because the number of trials is quite high, Because the definition of the Poisson distribution is that the number of trials increases infinite, right? So the 0.5 is very minor value for the answer from this normal approximation. So in this case, we don't have to use the correction factor, okay? So this will be the probability of Z when Z is smaller than or equal to 950 minus 1000 over root 1000, right? Right? Because the mean and variance have the identical value of lambda for the case of the Poisson distribution, right? So this can be written as the probability of Z when Z is smaller than or equal to minus 50, okay, over 31.62. So this is the probability of Z when Z is smaller than or equal to minus 1.58, okay? So by using the appendix table, the answer will be 0.057. So by using the normal approximation, we can simply calculate this very complicated Poisson distribution problem, okay? 그거는 만약에 문제에 포이슨이나 그렇게 나올 거예요. 포이슨 아니면 바이노미얼 디스트리뷰션을 표시해 줄 거예요. 근데 크고 작은 것에 대한 기준은 본인이 스스로 선택해야 되죠. 그죠? 그리고 하나 체크해야 될 게 포이슨 디스트리뷰션 같은 경우는 민하고 베리언스가 같아야 된다 라는 조건이 하나 더 있죠. 그죠? 그러니까 민하고 베리언스가 같다는 조건을 만족을 시키고 여기서 트라이얼 개수가 충분히 크다라고 본인이 판단이 되면 포이슨 디스트리뷰션을 쓰셔도 돼요. 바이노미얼 디스트리뷰션 안 쓰시고. 아시겠죠? So, I'm going to explain about the exponential distribution. And to explain about the exponential distribution, we have to first know about the Poisson distribution. And Poisson distribution defined a random variable as the number of flows along the wire. Okay? So this can be expressed by the flows per unit millimeter. That is the Poisson distribution, right? And what is the exponential distribution? Exponential distribution defines the random variable as the interval between flows, which means that millimeters, certain millimeters between flows. And this is an inverse with the Poisson distribution, okay? The Poisson distribution, we have to find out the number of flows, right? Right? When the length of wire is defined, okay? And the exponential distribution has the inverse relationship with the Poisson distribution, which means that we have to find out the interval length between flows, okay? So let the random variable x denote the length from any starting point on the wire until the first flow is detected. And let the random variable n denote the number of flows in x millimeters of wire. N has a Poisson distribution with mean lambda multiplied by x. Right? 여기서 유닛 랭스에 대해서 람다라고 정의를 했잖아요. 그죠? 그렇기 때문에 여기서는 x 밀리미터 와이어에 있는 플로우 개수를 선택해야 되니까 미는 람다 곱하기 x가 되겠죠? 그죠? 그죠? So in that case, what is the probability of x when x is larger than small x? That is the question. what is the definition of the x? X is the length from any starting point on the wire until the first floor is detected, right? And the n denotes the number of floors in x millimeter of wire, which means that if the large x is larger than small x, that should be equal to the probability of n when n is equal to 0, right? 큰 x가 첫 번째 플로우가 디텍팅 할 때까지 필요한 길이에요. 그죠? 그리고 n의 디파인이 플로우의 개수인데 그게 x랑 스몰 x만큼의 거리에 있을 때의 플로우 개수예요. 그럼 지금 이 x가 이 스몰 x보다 크잖아요. 그럼 퍼스트 플로우가 디텍팅하기 위해서 필요한 길이가 더 크다는 얘기죠. 그러면 n이 플로우 개수가 0이겠죠. 이해되세요? 다시 x는 길인데 첫 번째 플로우가 발생할 때까지 필요한 길이에요. 그죠? 그게 라지 x. 그리고 스몰 x는 이 스몰 큰 n을 디파인하기 위한 건데 이게 라지 n의 데피니션이 플로우의 개수인데 이게 스몰 x만큼 거리에서 있을 때의 플로우의 개수예요. 그런데 지금 퍼스트 플로우 찾을 때까지 필요한 x가 지금 더 크잖아요. 그러면 이 안에서 플로우가 발생할 확률은 제로죠. 그죠? 없겠죠. So the probability of x when x is larger than small x should be equal to the probability of n when n is equal to 0. Okay? And the n follows the Poisson distribution, right? Right? So this should be equal to e minus lambda x multiplied by lambda x to 0th power over 0 factorial, right? Okay? So this is equal to 1. This is equal to 1. So this should be exponential minus lambda x. Okay? And therefore, the cumulative distribution function of x is equal to large f large x is equal to the probability of x when x is smaller than or equal to small x, right? Right? That is the definition of the cumulative distribution function, right? So, what is this? That is 1 minus probability of x when x is larger than small x. Okay? So, that is equal to 1 minus e minus lambda x. Okay? By differentiating the cumulative distribution function, we can obtain the probability density function of x, right? So, if we differentiate the cumulative distribution function by x, the probability mass function will be minus lambda by e minus lambda x, right? Right? So this is equal to lambda by e minus lambda x. So that is the probability density function of the exponential distribution. Okay? Okay? 이거 x로 미분하면은 이거잖아요. 그죠? So the definition of the exponential distribution is as follows. The random variable x that equals the distance between successive events of a Poisson process with a mean lambda when lambda is larger than 0 is an exponential random variable with the parameter lambda. So the probability density function of x is fx is equal to lambda exponential minus lambda x when x is larger than or equal to 0. So this slide explains about the exponential distribution graphs. And this is the probability density function of exponential random variables for the selected values of lambda. And this is the probability density function, and this is the random variable. And according to the change of the lambda, we can have this kind of different curves, okay? And firstly, the y-intercept of the exponential probability density function is lambda, which means that the y-intercept here indicates the lambda value, okay? And the random variable is non-negative. X should be larger than or equal to 0. And extend to infinite, okay? So and x can increase infinite. And the cumulative distribution function fx is equal to 1 minus e minus lambda x, right here. It's well worth to memorize. Why? Because it is used often. And this is about the exponential mean and variance. If the random variable x has an exponential distribution with parameter lambda, the mean and variance are as follows. Mean is equal to 1 over lambda, and the variance sigma square is equal to 1 over lambda square, which means that the standard deviation is 1 over lambda, right? Because that is root sigma square. So it should be noted that in the case of the Poisson distribution, the mean and variance are the same value, right, as lambda. And in the case of the exponential distribution, the mean and standard deviation are the same as 1 over lambda. And this is the example. In a large corporate computer network, user logons to the system can be modeled as the Poisson process, Poisson distribution, with a mean of 25 logons per hour. Let x denote the time in hour from the start of the interval until the first logon. And what is the probability that there are no logons in the next 0.1 hour? This should be the probability of x when x is larger than 0.1, right? Right? And what is the probability density function for this case? That is lambda e minus lambda x, right? So this can be rewritten as, what is the lambda? Lambda is 25 here. 25 by exponential minus 25x. Okay? Okay? So this can be the integration fx dx from 0.1 to infinite. Right? Right? And this can be written as the integration 25 e minus 25 x dx from 0.1 to infinite. Okay? Okay? And this will be minus e minus 25 x from 0.1 to infinite. That is equal to e minus infinite minus e minus 25 by 0.1. Okay? What is this? It's equal to 0. So the answer will be e minus 2.5. Okay? So this is 0.082. And also, we can simply calculate this equation in different ways. The probability of x when x is larger than 0.1 is equal to 1 minus the probability of x when x is smaller than or equal to 0.1, right? Right? And this will be 1 minus the cumulative distribution function f 0.1. Okay? And this is 1 minus e minus 25 by 0.1, right? That is the cumulative distribution function. Fx is equal to 1 minus e minus lambda x. So 1 can be eliminated. So finally the answer will be e minus 2.5. That is equal to 0.082. So based on this cumulative distribution function, we can also calculate the answer, okay? And continuing, what is the probability that the time until the next log on is between 0.033 and 0.05 hours? This will be the probability of x when x is between 0.033, 0.05, right? And this will be the integration 25 e minus 25 x dx from 0.033 to 0.05. And this will be minus e minus 25x from 0.033 to 0.05. This will be minus e minus 25 by 0.05 minus e minus 25 by 0.033. If you calculate this based on the scientific calculator, the answer will be 0.152. Okay? And continuing, what is the interval of time such that the probability that the log on occurs during the interval is 0.9. This should be the probability of x when x is larger than small x, right? Right? So they should be equal to 0.9. Okay? So that is integration 25 e minus 25 x dx from x to infinite. Okay? And this is equal to minus e minus 25 x from x to infinite. This will be minus e minus infinite plus e minus 25x, right? This should be equal to 0. So the e minus 25x should be equal to 0.9. Okay? Okay? And if we provide the ln for both sides, what is this? Minus 25x, right? And this will be ln 0.9, okay? So the x is equal to ln 0.9 over minus 25. That is minus 0.10536 over minus 25. That is equal to 0.00921 hour. So this means that the probability that there will be no log on within the first 0.00421 hour is 0.9. Okay?